Right now, I'll be presenting about the task 3, which is the object detection with AI custom dataset. Alright, so for this task 3, it is a task where we need to do a real-time object detection system of a traffic light using the Microros Pi-Fi robot car. Alright, so here comes to our first task that we need to do in task 3 actually. Um, It is more focused on the data collections where we have recorded the traffic light using our smartphone camera, and we recorded it through multiple perspective, also under different lighting conditions. To have a high brightness or low brightness, the perspective I would say maybe from a different angle, and then also from a different distance, a data set setup. So as you can see here is a dataset annotation. As the first step, we basically annotate only the top part actually for the traffic light. So for each dataset, we are doing the same thing because our target is only to capture the shape of our object. And after that, we are doing a version creation. So for this version creation, we do a split proportions for our datasets. 70% of it consists of trend dataset, 20% of it contains a valid dataset, and the last one is a 10% of test set. And after that, we are configuring the pre-processing and augmentation. Third step in this task, which is model training. And you can see in the slide, the first one is a model architecture, which is with using a RoboFlow 3.0. And after that, we use a model size fast. And after that is we use the training from a public checkpoint where we are using the pre-trained benchmark model, where it is actually from the RoboFlow universe. There are a lot of model that have been published there. So for this training, we are using the benchmark from there. And you can see in the image in this slide, it is actually the current performance of our model training. You can see that it actually goes well. You can see that the positions in the matrix, it has a high percentage, and you can see that the graph below, the name of it is a model performance, and it starts at the bottom and then it stays at height, and it stays flat there. So I would say that even though we're using model size fast, the performance is surprisingly good. So that's why we proceed to use this type of model size. All right. So for the next step is we are proceeding to a model deployment. We need to start with the very first step, which is a dependencies installation. So a PyTorch dependency, which is a main framework for a YOLO V8 and model, was installed on the Pi-Fi. So the next one is creates a ROS2 detection node. So it was the ROS2 node was written in the Python, and it is necessary to complete the real-time detection process. So this node was subscribed to one topic. The next one is inference test. So during the callback, the incoming image was converted from ROS message format to OpenCV format through the CV bridge. So the image will be the input into the YOLO V8 model, which was loaded through the PyTorch, and the prediction result, which contain the bounding boxes, the confidence scores, and also the class labels were written. So this written result will be put into the original image through OpenCV drawing functions for a visual output. So after that, the next step is a Docker container. So this container can actually reduce the issues during the installation and execution by providing a repeatable or a portable environment. All right. So the last one for this step four is will be publish the result. All right. So now we are moving to the last part, which is a result for task three. So in this image, in the slides, it consists of map, which is a mean, average, precision, three type of component, which is a box loss, class loss, and object loss. So on the top graph, you can see that a solid purple line and a lighter purple line. For the solid purple line, it means or it shows that a predicted bounding box which consider correct. The first loss component is a box loss. The box loss easily means that the model is quickly learning the bounding box coordinates, and the class loss is the result of near zero classification loss after epoch is equal to 100. The last graph, which is the object loss, it shows the evaluation of how confident our model is with the detections. It started out low but steadily decreased over the time of training, which implies that the model is gaining more certainty in its more accurate over training epochs. So the first one is actually a video that shows the detections of our model, and we can see that it accurately detects, and we actually have a threshold of the confidence over the 90%.
So back at it again. So yeah, like with but like I've said, and task one and task two, and also task three, Fidos also said there will be some problems arises. So yeah, because the robot may be faulty, and it is because of the surrounding factor, and the task is not so-called perfect in terms of execution. Also, the results, eh, this is because of those limitations. Okay. Under task one and task two, so what I've seen, the problem in task one and task two is, yes, one is connectivity. So to connect with the bot is it's a hassle. We need to like very try hard to find a connection. Also, the hotspot, sometimes it doesn't appear on our device. I don't know why, because yeah, it's maybe something with electronic stuff. And secondly, it's very major. It's a hardware issue, and that is the wheel keeps getting off. Um, I I can say that all wheel, all four wheels has detached whenever we do some uh, simulations. But the major one is the rear left. It always detached. So this is the major issue. Whenever like I've mentioned, the smoother surface basically makes the wheel like slips. But in this case, the wheel is not slipping because the surface is very rough, so the friction is very high. So instead of the wheel is slipping to make a turn, it's the shaft, the axle. The axle is slipping between the wheel. So it's like there's a force actually making the wheels detached. So lastly, there's an input lag. Whenever like we press, it's a keyboard control. Then we press like maybe it's a JKL. Maybe K is stop. No, no, no. L is like turning right. It takes like uh hundreds of milliseconds maybe, and then after that it starts to do something. So yeah, like I said, the implications, we cannot maneuver it tightly. We cannot maneuver it according to our needs and liking. Yes, the wheels keeps detached, and lastly, the car is not agile. But that's not the biggest issue. It's just uh very frustrating. But these are some of the learning path and learning ways. So this is the video of line tracking, line follow. So whenever the bot is placed on a straight path, it tries to follow, but then when it start when the path is starting to curve, it wants to curve, it wants to like turn corner, but the the hardware itself, the wheels doesn't cooperate. So the inner wheel slippings instead of if in this case uh we want to turn left. So the outer tire should spin forward, and the inner tire should like maybe stop or spin backwards. Ah, so it creates a turn. But in this case, uh maybe the inside tire of rear left tries to stop or maybe spins backward, but instead it doesn't stop. The wheel just we can see that it's just spinning and eventually came off. So we can see that it overshoot. So yeah, that's the end of the simulation of line follow. It detects the obstacle. It starts beeping.
So, there are a few of the practical issues and constraints that happen during the development of our object detection setup in RoboFlow platform. So, the first one is actually limited RoboFlow credits. So, with the insufficient credits, there were not enough left for us um, to conduct more experiments. So that is the implications. After that is a problem regarding the server response times. So the implication of this problem is that it shows a significant latency. So the third problem is the annotation error. So actually, when we are preparing to retrain back the model of earlier version that we have created before this, a few of bounding boxes shifted and doesn't match its original position. So the implication is it could result to the treble model performance. So that is the problems regarding the task tree. I think that's all.
Also, for the conclusion, this project proved that the Yahoo Micro ROS Pi 5 robot car that it can handle the manual control, autonomous navigation, and also the AI detection using the limited hardware. This project highlights that the complex robotics are achievable on low-cost platforms while offering hands-on experience in integration, debugging, and sensing, with the future potential for the speech, control, cloud connectivity, and also the LiDAR mapping. That's all. Thank you, everyone. Schluss.